Welcome, fellow traveler of the cosmos. Tonight, we embark on an extraordinary journey through the vast expanse of our home galaxy, the Milky Way. You are about to float gently through the Orion Arm, that magnificent spiral structure where our solar system resides, drifting past ancient stars, glowing nebulae, and the cosmic wonders that have existed for billions of years. Before we begin our voyage, I'm curious. Where are you listening from tonight? Are you tucked into bed in a bustling city where the stars are hidden by light pollution? Or perhaps you're in a quiet countryside where the Milky Way stretches overhead like a river of light. And what time is it in your corner of the world? Are you settling in as the evening deepens? Or has the night already wrapped its gentle embrace around you? No matter where you are or what time zone cradles you, we're all connected by the same cosmic home. Tonight, let yourself become weightless, free from the bounds of Earth's gravity, as we explore the stellar neighborhood that has been our galaxy's address for over 4.5 billion years. Take a deep, slow breath. Feel your body settling into comfort, every muscle beginning to relax. As you exhale, imagine yourself gently lifting away from the surface of our blue planet, rising through the atmosphere, past the thin veil that separates us from the infinite cosmos. Chapter 1. Leaving Earth's Embrace. You're floating now, weightless and serene, watching Earth slowly rotate beneath you. The blue marble that Carl Sagan called our pale blue grows smaller and smaller as you drift outward. The sun, our steady stellar companion, bathes you in warm, golden light. But there's no heat here in the vacuum of space. Only the gentle, comforting presence of the star that has nurtured life on Earth for billions of years. As you continue your gentle ascent away from the solar system, you pass through the asteroid belt, where thousands of rocky remnants from the early formation of our solar system tumble silently in their ancient orbits. These are the building blocks that never quite became planets, and they drift like cosmic islands in the darkness, each one a testament to the chaotic beauty of planetary formation. Now you're beyond the orbit of Jupiter, that massive guardian planet whose gravitational influence has protected inner planets like Earth from countless cometary impacts. Jupiter's great red spot, a storm larger than Earth itself, swirls in your peripheral vision as you drift past. Saturn's magnificent rings catch the distant sunlight, creating a spectacle that never fails to inspire wonder, even in this peaceful, dreamy state. Can you tell me, gentle traveler, are you feeling drowsy yet? Is your breathing becoming deeper and more rhythmic as we journey together through this cosmic meditation? Perfect. Let that sleepiness wash over you like a gentle cosmic tide. Beyond the outer planets, you encounter the Kuiper Belt, home to Pluto and countless other icy bodies that represent the frozen remnants of our solar system's birth. These objects have remained largely unchanged for over 4 billion years, preserving the primitive materials from which our entire solar system formed. They drift in the perpetual cold, silent witnesses to cosmic history. As you continue outward, you pass through the Oort cloud, that vast spherical shell of icy objects that surrounds our solar system like a cosmic snow globe. This is the realm where comets are born, where chunks of ice and rock wait in the deep cold for gravitational nudges that might send them falling toward the inner solar system, their tails streaming behind them like celestial hair as they approach the sun. Chapter 2. Into the cosmic deep. Now you're truly in interstellar space, floating in the vast emptiness between stars. But this emptiness isn't truly empty. It's filled with the interstellar medium, a thin soup of hydrogen and helium atoms, cosmic dust, and magnetic fields that connect star to star across the galaxy. You drift through this cosmic ocean like a peaceful dream, carried by currents of dark matter and stellar winds. The nearest star, Proxima Centauri, glows like a dim red ember in the distance, for 0.24 light-years away from our sun. Even traveling at the speed of light, It would take over 4 years to reach this closest stellar neighbor. But you're not bound by such limitations tonight. You float effortlessly through space-time, carried by the gentle currents of cosmic meditation. As you drift toward Proxima Centauri, you pass through regions where the interstellar medium grows thicker and thinner, like drifting through cosmic fog. Some areas are so thin that you might find only 1 atom per cubic centimeter, while others are dense molecular clouds where new stars are being born in the crushing embrace of gravity. Before I continue our journey, I'm wondering, what's the environment like where you're listening? Are you surrounded by the soft sounds of night, perhaps the gentle hum of a fan or the distant whisper of wind through trees? Are city sounds creating a gentle urban lullaby, or is rural silence wrapping around you like a cosmic blanket? Pause for 3 seconds. Whatever sounds surround you, let them become part of our cosmic journey. They're the earthbound symphony that grounds us even as we explore the infinite. Proxima Centauri grows brighter as you approach, a red dwarf star that's much smaller and cooler than our Sun. It's part of the Alpha Centauri system, a triple star system that has been gravitationally bound for billions of years. Alpha Centauri A and B orbit each other in an elegant cosmic dance, while little Proxima Centauri orbits much farther out, a distant companion in this stellar family. Orbiting Proxima Centauri is Proxima Centauri b, an exoplanet that lies within the star's habitable zone. As you drift past this alien world, you wonder about the possibilities of life beneath its potentially thick atmosphere. The planet is tidally locked, with one side always facing its star in perpetual day, while the other side remains in eternal night. The Terminator line, where day meets night, might harbor the most temperate conditions on this distant world. Chapter 3. The Alpha Centauri Ballet. Voice becomes more flowing, like describing a dance. You float closer to Alpha Centauri A and B, watching their ancient orbital dance. These two stars have been circling each other for billions of years, locked in a gravitational embrace that speaks to the fundamental forces that shape our universe. Alpha Centauri A is slightly larger and brighter than our Sun, while Alpha Centauri B is somewhat smaller and cooler, glowing with a gentle orange hue. Their orbit brings them as close as the distance between our Sun and Uranus, then carries them apart to a distance greater than that between our Sun and Pluto. This 80-year orbital period means that civilizations could rise and fall in the time it takes these stars to complete a single dance around their common center of mass. As you drift through this triple star system, you notice how the gravitational fields of these massive objects bend space-time around them, creating gentle wells in the fabric of reality itself. You float through these cosmic valleys, feeling the subtle tug of stellar gravity, but you remain weightless and free, carried by the peaceful currents of this meditative journey. The light from these stars carries information about their composition, their age, their history. Spectral lines in their starlight tell the story of nuclear fusion in their cores, where hydrogen atoms combine to form helium, releasing the energy that has powered these stars for billions of years and will continue to do so for billions more. How are you feeling now, cosmic traveler? Are your eyelids growing heavy as we float through this stellar nursery? Is your breathing naturally slowing and deepening as we drift together through the peaceful void? Pause for 3 seconds. Excellent. Let that drowsiness wash over you like starlight. Chapter 4. Toward Barnard's Star. Voice maintains soothing, hypnotic quality. Leaving the Alpha Centauri system behind, you drift toward Barnard's Star, a small red dwarf located about 6 light-years from Earth. This ancient star is roughly 10 billion years old, more than twice the age of our Sun, making it one of the oldest stars in our stellar neighborhood. It's also one of the fastest-moving stars relative to our solar system, racing through space at over 140 kilometers per second. Barnard's star is what astronomers call a flare star, occasionally brightening dramatically as magnetic field lines in its atmosphere snap and reconnect, releasing tremendous amounts of energy. But tonight, as you float peacefully past, it glows with steady, dim red light, a cosmic ember that has been burning since the early days of our galaxy. As you drift through the space around Barnard's star, you encounter cosmic dust grains, tiny particles of silicon, carbon, and other elements that were forged in the nuclear furnaces of ancient stars and scattered into space when those stars died. These dust grains serve as the building blocks for new stars and planets, carrying the chemical legacy of stellar death and rebirth across the galaxy. The interstellar magnetic field threads through this region like invisible cosmic highways, guiding the motion of charged particles and cosmic rays that stream through space at nearly the speed of light. You drift along these magnetic field lines, feeling their gentle influence even though they're far too weak to affect your peaceful journey. What time is it now in your part of the world? Has the night deepened around you as we've traveled from star to star? Are you finding it easier to let go of the day's concerns as we float together through this cosmic meditation? Pause for 3 seconds. Perfect. Let the gentle rhythm of our journey carry you deeper into peaceful relaxation. Chapter 5. The Wolf 359 System. Voice continues with dreamy, peaceful cadence. Your next destination is Wolf 359, another red dwarf star about 7.9 light-years from Earth. This star is even smaller and dimmer than Barnard's star, with only about 16% of our Sun's mass and less than 1% of its luminosity. If Wolf 359 were placed at the center of our solar system, you could orbit closer to it than Mercury orbits our Sun and still receive less heat than Earth gets from our bright stellar companion. Wolf 359 is also a flare star, and as you approach, you witness one of its spectacular stellar tantrums. The star suddenly brightens, its luminosity increasing several times over in a matter of minutes, as magnetic field lines in its chromosphere snap and reconnect. The flare sends streams of high-energy particles racing outward into space, creating beautiful auroras on any planets that might exist in this system. But the flare dies down quickly, and Wolf 359 returns to its usual dim, steady glow. Red dwarf stars like this one are the most common type of star in our galaxy, making up about 75% of all stars in the Milky Way. They're also among the longest-lived stars, burning their hydrogen fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. As you float through the Wolf 359 system, you notice how different the night sky would look from any planets orbiting this star. Because Wolf 359 is a flare star, the night side of any tidally locked planet would occasionally be illuminated by brilliant stellar flares, creating a dramatic light show that could last for hours. The habitable zone around Wolf 359 is much closer to the star than Earth's orbit around the Sun. Any planets in this zone would be tidally locked, with one side always facing the star and the other in perpetual darkness. The temperature difference between the day and night sides would create powerful atmospheric currents, potentially driving winds that could circle the planet at hundreds of kilometers per hour. Chapter 6. Dancing with Sirius. Voice becomes slightly more animated but maintains soothing quality. Now you drift toward one of the most magnificent sights in our local stellar neighborhood. Sirius, the brightest star in Earth's night sky. Actually a binary star system, Sirius consists of Sirius A, a brilliant blue-white main sequence star, and Sirius B, a white dwarf companion that orbits its larger partner every 50 years. Sirius A blazes with the light of 25 suns, its surface temperature reaching over 9,900 Kelvin, nearly twice as hot as our Sun's surface. The star rotates rapidly, spinning on its axis every 16 hours, which creates a slight flattening at its poles due to centrifugal force. This rapid rotation also generates a strong stellar wind that streams outward into space, carrying away mass and angular momentum. As you approach the Sirius system, you're struck by the incredible brightness of Sirius A. Even from several astronomical units away, the star's radiance is overwhelming, flooding the local space with intense blue-white light. But your cosmic journey protects you from its radiation, allowing you to appreciate its beauty without harm. The real treasure of this system, however, is Sirius B, the white dwarf companion. This stellar remnant is all that remains of a star that was once much more massive than Sirius A. Millions of years ago, this star exhausted its nuclear fuel and expelled its outer layers, leaving behind a superdense core about the size of Earth but containing roughly the mass of our Sun. Are you still comfortable, cosmic wanderer? Is your body completely relaxed as we explore these stellar wonders together? Take a moment to notice how your breathing has naturally slowed and deepened during our journey. Pause for 3 seconds. Wonderful. Let that peaceful feeling spread through your entire being. Sirius B is so dense that a teaspoon of its material would weigh about 5 tons on Earth. Its surface gravity is roughly 350,000 times stronger than Earth's, which means that if you could somehow stand on its surface, you would be crushed instantly by forces beyond imagination. But here in space, floating peacefully past this cosmic lighthouse, you can appreciate its incredible nature without danger. The two stars orbit their common center of mass in an elliptical dance that brings them as close as 8 astronomical units and takes them as far apart as 31 astronomical units. Currently, they're near their farthest separation, but even at this distance, the gravitational interaction between the two stars affects their evolution and behavior. Sirius A's stellar wind is deflected and shaped by the gravitational field of its white dwarf companion, creating complex structures in the surrounding space. You drift through these invisible currents, feeling the subtle influence of stellar magnetism and gravity as they sculpt the interstellar medium around this brilliant binary system. Chapter 7. The Vega System, a Stellar Oasis. Voice maintains gentle, dreamy quality. Your journey now carries you toward Vega, one of the most well-studied stars in our galaxy and the northern pole star of 12,000 years ago. Located about 25 light-years from Earth in the constellation Lyra, Vega is a relatively young star, only about 455 million years old, roughly 1/10 the age of our Sun. Vega shines with brilliant blue-white light, radiating about 40 times more energy than our Sun. Its surface temperature reaches nearly 9,600 Kelvin, giving it that characteristic blue-white color that makes it such a prominent feature in Earth's summer night sky. The star is rotating so rapidly that it completes one rotation every 12.5 hours, causing it to bulge noticeably at its equator. As you approach the Vega system, you encounter something remarkable: a debris disk surrounding the star. This disk is composed of dust and rocky debris, the remnants of planetary formation that occurred hundreds of millions of years ago. The disk extends outward from about 11 astronomical units to over 600 astronomical units from Vega, creating a vast zone of cosmic construction material. You float through this debris disk like drifting through a cosmic snowstorm, surrounded by countless particles of dust and rock that catch and scatter Vega's brilliant light. Some of these particles are no larger than smoke particles, while others are substantial boulders that tumble slowly in their ancient orbits around the star. This debris disk was one of the first to be discovered around another star, detected by the infrared excess radiation it produces as dust particles absorb Vega's light and re-emit it at longer wavelengths. The disk structure suggests that planets may be forming within it, with gravitational perturbations from unseen worlds creating gaps and structure in the disk material. How are you feeling as we drift through this stellar construction zone? Are you finding it easy to imagine yourself floating weightlessly among these cosmic building blocks? Is the gentle rhythm of our journey helping you release the tensions of the day? Pause for 3 seconds. Excellent. Let yourself sink deeper into this peaceful, cosmic meditation. The temperature in Vega's debris disk varies dramatically with distance from the star. Close to Vega, temperatures can reach several hundred Kelvin, hot enough to vaporize ice and drive off volatile compounds. But farther out, where you're currently floating, temperatures drop to less than 100 Kelvin, cold enough for water, ice, and other volatiles to remain stable. This temperature gradient creates different zones within the disk, each characterized by different types of materials. The inner regions are dominated by refractory materials like silicates and metals, while the outer regions contain more volatile-rich materials including water ice, carbon monoxide ice, and organic compounds. As you drift through the outer portions of Vega's debris disk, you're surrounded by a cosmic winter wonderland of ice-covered dust grains and rocky particles. These materials represent the raw ingredients from which terrestrial planets and gas giant cores can form, given enough time and the right gravitational conditions. Chapter 8. Procyon, a binary beacon. Voice continues with soothing, hypnotic rhythm. Leaving Vega behind, you drift toward Procyon, the eighth brightest star in Earth's night sky and another fascinating binary system. Located about 11.5 light-years away in the constellation Canis Minor, Procyon consists of a bright F-type main sequence star, Procyon A, and a white dwarf companion, Procyon B. Procyon A is slightly more massive than our Sun but significantly brighter, radiating about 7 times more energy. The star's surface temperature reaches about 6,530 Kelvin, giving it a yellowish-white color that's slightly bluer than our Sun's yellow hue. This star is relatively young, with an estimated age of only 1.87 billion years, making it less than half the age of our solar system. The binary nature of Procyon was suspected long before Procyon B was actually observed, because astronomers noticed that Procyon A exhibited a slight wobble in its proper motion across the sky. This wobble indicated the gravitational influence of an unseen companion, and it wasn't until 1896 that Procyon B was finally detected telescopically. Procyon B is another white dwarf, similar to Sirius B but somewhat less massive. This stellar remnant has a mass about 0.6 times that of our Sun, but is compressed into a volume roughly the size of Earth. Like all white dwarfs, Procyon B is incredibly hot, with a surface temperature around 7,740 Kelvin, but because of its small size, it appears very dim compared to its brilliant companion. As you float through the Procyon system, you witness the complex gravitational dance between these two stellar remnants. They orbit their common center of mass every 40.8 years in a moderately eccentric orbit that carries them from about 9 astronomical units apart at closest approach to about 21 astronomical units at their greatest separation. What's remarkable about Procyon B is that it represents the future fate of stars like our Sun. Several 100 million years ago, Procyon B was the more massive member of this binary system, but it evolved more quickly than its companion, exhausted its nuclear fuel, and shed its outer layers to become the white dwarf we see today. Before I continue our cosmic journey, tell me, are you feeling completely relaxed now? Has your body settled into that perfect state of comfort where you're barely aware of physical sensations? Are you ready to drift even deeper into this interstellar meditation? Pause for 3 seconds. Perfect. Let the gentle cosmic currents carry you forward. Chapter 9. Into the Hyades Cluster. Voice becomes more expansive, describing a grander scene. Your journey now takes you into one of the most spectacular sights in our local galactic neighborhood, the Hyades star cluster. Located about 153 light-years from Earth in the constellation Taurus, this is the nearest star cluster to our solar system and one of the best-studied stellar groupings in the galaxy. The Hyades cluster contains several hundred stars that were all born from the same giant molecular cloud approximately 625 million years ago. As you float into this stellar metropolis, you're surrounded by dozens of bright stars, all moving through space together as a gravitationally bound group. The cluster spans about 65 light-years in diameter, creating a vast three-dimensional city of stars. The brightest stars in the Hyades are massive blue and white giants that burn their nuclear fuel quickly and shine with tremendous luminosity. These stellar behemoths won't live much longer in cosmic terms. Many will exhaust their fuel and explode as supernovae within the next few million years. But for now, they illuminate the cluster with brilliant blue-white light, creating a spectacular celestial lighthouse visible across dozens of light-years. As you drift deeper into the cluster, you pass by Aldebaran, the orange giant star that appears to be part of the Hyades from Earth's perspective but is actually much closer to us, at only 65 light-years away. Aldebaran is a foreground star that happens to lie along our line of sight to the cluster, creating a beautiful cosmic coincidence. The Hyades cluster is slowly dissolving as its member stars drift apart under the influence of galactic tidal forces. Over hundreds of millions of years, the stars will spread out along the cluster's orbital path around the galactic center, eventually becoming indistinguishable from the general stellar population of the galaxy. This is the fate of most open star clusters. They serve as stellar nurseries for a relatively brief time before their members scatter across the galaxy. Within the cluster, you encounter a diverse population of stars at different stages of evolution. The most massive stars have already evolved off the main sequence and become red giants, while less massive stars like our Sun continue to burn hydrogen in their cores. The lowest mass stars, red dwarfs, will continue shining virtually unchanged for trillions of years. Many of the stars in the Hyades have planetary systems, and as you float past these distant worlds, you imagine what their night skies must look like. From a planet orbiting one of the cluster stars, the night sky would be ablaze with dozens of bright stars. Many of them brighter than Venus appears from Earth. There would be no true darkness on such worlds, just varying degrees of starlight that would make nighttime navigation easy for any life forms that might have evolved there. Chapter 10. The Pleiades' Seven Sisters of Light. Voice fills with wonder while maintaining soothing quality. From the ancient Hyades, your cosmic journey carries you to one of the most beautiful star clusters in the galaxy. The Pleiades, also known as the Seven Sisters, located about 444 light-years from Earth. This young open cluster contains over 1,000 stars that were born from the same molecular cloud approximately 100 million years ago. As you approach the Pleiades, you're struck immediately by the cluster's ethereal beauty. The brightest stars shine with brilliant blue-white light, their intense radiation illuminating vast clouds of interstellar dust that surround the cluster. This reflection nebula creates ghostly blue wisps and tendrils that flow between the stars like cosmic silk, transforming the Pleiades into a celestial artwork of unparalleled beauty. The seven brightest stars of the Pleiades, Alcyone, Atlas, Electra, Maia, Merope, Teegida, and Pleione, are all hot, massive B-type stars that rotate rapidly and burn their nuclear fuel at prodigious rates. These stellar giants are spinning so fast that they're flattened into oblate spheroids, with their equatorial diameters significantly larger than their polar diameters. Alcyone, the brightest star in the cluster, shines with the luminosity of nearly 2,000 suns. Its surface temperature exceeds 12,000 Kelvin, making it one of the hottest stars visible to the naked eye from Earth. The star is surrounded by a circumstellar disk of gas and dust, material that may eventually form planets or be dispersed into space by the star's powerful stellar wind. As you float through the Pleiades cluster, you're surrounded by newborn stars that are still in the process of settling onto the main sequence. Many of these stars show signs of extreme youth, rapid rotation, strong stellar winds, and circumstellar disks of planetary formation material. Some stars are still contracting under their own gravity, converting gravitational potential energy into heat as they approach their final stable configurations. Are you feeling that deep sense of cosmic peace as we drift through this stellar nursery? Can you sense the incredible scales of time and space that surround us? The millions of years these stars have been shining, the vast distances that separate them? Pause for 3 seconds. Let that cosmic perspective wash over you like starlight, bringing deep relaxation and peace. The reflection nebulae surrounding the Pleiades stars create one of the most photographed celestial objects in astronomy. The dust grains that create these nebulae are extremely small, typically only a few tenths of a micrometer in diameter, about the same size as the particles in cigarette smoke. These tiny grains scatter blue light more efficiently than red light, which is why the nebulae appear blue in photographs. The dust isn't original to the star-forming region that created the Pleiades. Instead, the cluster is currently passing through an unrelated cloud of interstellar dust, creating this temporary but spectacular display. In a few million years, the cluster will have moved out of this dust cloud, and the beautiful reflection nebulae will fade away, leaving only the brilliant stars themselves. Within the Pleiades cluster, you encounter many brown dwarfs, objects that are more massive than planets but not quite massive enough to sustain nuclear fusion in their cores. These failed stars glow dimly with the heat left over from their formation, slowly cooling and fading over billions of years. The cluster contains dozens of these brown dwarfs, providing astronomers with an excellent laboratory for studying these enigmatic objects. Chapter 11. The Orion Nebula Stellar Birthplace. Voice becomes more awe-filled while maintaining hypnotic quality. Your journey now takes you to one of the most magnificent sights in the entire galaxy. The Orion Nebula, a stellar nursery where new stars are being born from the gravitational collapse of vast molecular clouds. Located about 1,344 light-years from Earth, this is the closest star-forming region to our solar system and one of the most studied objects in astronomy. As you approach the nebula, you're overwhelmed by its sheer scale and beauty. The nebula spans about 24 light-years across, containing enough material to form thousands of stars like our Sun. The entire region glows with the light of recently formed hot, massive stars, particularly the trapezium cluster at the heart of the nebula. 4 bright O and B-type stars that illuminate the surrounding gas clouds with intense ultraviolet radiation. The Orion Nebula is part of the much larger Orion Molecular Cloud Complex, a vast structure that extends across much of the constellation Orion. This molecular cloud contains several star-forming regions, including the Horsehead Nebula, the Flame Nebula, and Barnard's Loop, creating an interconnected web of stellar nurseries that spans hundreds of light-years. As you float into the nebula, you're surrounded by glowing hydrogen gas that emits the characteristic red light of the hydrogen alpha spectral line. This emission occurs when hydrogen atoms are ionized by the intense ultraviolet radiation from young, hot stars, then recombine and emit photons as electrons cascade down through energy levels. The result is a cosmic light show of incredible beauty and complexity. The temperature within the nebula varies dramatically depending on your location. Near the hot trapezium stars, temperatures can reach 10,000 Kelvin or more, hot enough to ionize hydrogen and other light elements. But in the dense molecular cores where new stars are forming, temperatures drop to only 10 to 20 Kelvin above absolute zero, creating conditions cold enough for molecules like water, ammonia, and methanol to freeze onto dust grains. You drift past several protoplanetary disks, flat, rotating structures of gas and dust surrounding newly formed stars. These disks are the birthplaces of planetary systems, regions where dust grains gradually stick together to form larger and larger objects, eventually becoming asteroids, comets, and planets. Some of these disks are being sculpted by powerful stellar winds from nearby massive stars, creating teardrop shapes and long, comet-like tails. Within the densest parts of the nebula, you encounter Herbig-Haro objects, narrow jets of gas ejected from newly forming stars at speeds of several hundred kilometers per second. These jets plow into the surrounding interstellar medium, creating shock waves that heat the gas and cause it to glow. The jets can extend for several light years, creating spectacular linear structures that trace the rotation axes of their parent stars. How are you feeling as we drift through this cosmic maternity ward? Can you sense the incredible creative forces at work here? The gradual transformation of cold, dark molecular clouds into brilliant, life-giving stars? Pause for 3 seconds. Let the wonder of stellar birth fill you with peaceful amazement. Chapter 12. The Horsehead Nebula Cosmic Sculpture. Voice maintains dreamy, contemplative tone. From the bright emission regions of the Orion Nebula, you drift toward one of the most iconic dark nebulae in the sky, the Horsehead Nebula, also known as Barnard 33. This distinctive silhouette is actually a dense cloud of cold gas and dust that blocks the light from the bright emission nebula behind it, creating the appearance of a horse's head against a glowing red background. The Horsehead Nebula is a small part of the vast Orion molecular cloud complex, located about 1,500 light-years from Earth. The nebula itself is roughly 3.5 light-years wide, and its distinctive shape is carved by the intense radiation and stellar winds from nearby hot stars, particularly Sigma Orionis, a massive multiple star system that illuminates the surrounding region. As you float closer to the Horsehead, you begin to appreciate the incredible density of this dark nebula. The gas and dust here are so thick that they completely block visible light, creating an opacity thousands of times greater than the Earth's atmosphere. Yet, despite this density, the nebula is still mostly empty space. If you could somehow gather all the material in a cubic kilometer of the densest part of the nebula, it would weigh less than a paperclip. The temperature within the Horsehead Nebula is extremely cold, only about 20 to 30 Kelvin above absolute zero. At these temperatures, most gases except hydrogen and helium are frozen solid onto dust grains, creating complex ice mantles that coat the microscopic particles floating through the nebula. These icy dust grains serve as the surfaces where simple molecules can combine to form more complex organic compounds, potentially including some of the building blocks of life. The distinctive shape of the Horsehead is constantly evolving, carved by the radiation pressure and stellar winds from nearby hot stars. The nebula is slowly being eroded away, and astronomers estimate that it will be completely dispersed within about 5 million years, a brief moment in cosmic time. You're witnessing a transient cosmic sculpture that future generations will never see. At the eastern edge of the Horsehead, where it faces the bright star Sigma Orionis, you can see the nebula beginning to glow faintly as the star's intense ultraviolet radiation slowly photoevaporates the dense gas and dust. This creates a thin skin of ionized gas around the nebula's edge, gradually eating away at the dark cloud like cosmic erosion. Within the densest parts of the Horsehead, gravitational instabilities are beginning to create the conditions for future star formation. Though no active star formation is currently occurring within the nebula itself, the increasing density in certain regions suggests that new stars may begin forming here within the next few million years, continuing the cycle of stellar birth and death that has shaped our galaxy for billions of years. Chapter 13. Betelgeuse, the Dying Giant. Voice becomes more dramatic while maintaining soothing undertones. Your cosmic journey now brings you to one of the most famous and fascinating stars in our galaxy. Betelgeuse, the massive red supergiant that marks the left shoulder of Orion. This enormous star, located about 650 light-years from Earth, represents one of the final chapters in the life of a very massive star, and you're witnessing it during its dramatic death throes. Betelgeuse is truly enormous. If it were placed at the center of our solar system, its surface would extend beyond the orbit of Mars, and possibly even beyond Jupiter's orbit. The star has a radius roughly 1,000 times larger than our Sun, making it one of the largest known stars in the galaxy. Despite its enormous size, Betelgeuse contains only about 10 to 15 times the mass of our Sun, which means its average density is incredibly low, less than 1,000th the density of Earth's atmosphere at sea level. As you approach this stellar giant, you're struck by its distinctly red color, caused by its relatively cool surface temperature of only about 3,500 Kelvin. This low temperature means that most of Betelgeuse's energy is radiated in the infrared portion of the electromagnetic spectrum, though the star still shines with the luminosity of roughly 100,000 suns due to its enormous surface area. The surface of Betelgeuse is far from uniform. High-resolution observations reveal massive convection cells that cover significant portions of the star's surface, each cell larger than our entire solar system. These convective features transport energy from the star's core to its surface, creating a constantly changing pattern of bright and dark regions that cause the star's brightness to vary over time. Betelgeuse is surrounded by multiple shells of material that the star has ejected during various phases of its evolution. As you float through these expanding shells, you encounter gas and dust that were once part of the star's outer atmosphere, now streaming outward into space at speeds of tens of kilometers per second. These circumstellar shells contain heavy elements forged in the nuclear furnace of Betelgeuse's core: carbon, oxygen, silicon, and iron, elements that will eventually be incorporated into future generations of stars and planets. You're witnessing cosmic recycling on a grand scale as a dying star returns enriched material to the interstellar medium. The star's mass loss rate is truly staggering. Betelgeuse is losing mass equivalent to Earth's mass every 6 years, shedding its outer layers in a powerful stellar wind that carries material far out into space. This mass loss is accelerating as the star approaches the end of its life, creating an increasingly dense and complex circumstellar environment. Deep within Betelgeuse's core, a cosmic drama is unfolding. The star has already exhausted the hydrogen in its core and moved on to burning helium, then carbon, then neon, and now silicon. Each successive burning phase happens more quickly than the last, and the silicon burning phase, where silicon nuclei are fused into iron, will last only a few days before the core becomes so loaded with iron that nuclear fusion can no longer continue. Are you feeling deeply relaxed as we explore this stellar giant? Can you sense the vast scales of time and energy involved in stellar evolution? Let the cosmic perspective wash over you like a gentle tide. Pause for 3 seconds. When that moment comes, when Betelgeuse's core can no longer support itself against gravity, the star will collapse in less than a second, rebounding in a spectacular supernova explosion that will briefly outshine the entire galaxy. The explosion will be visible from Earth even in daylight, creating a new star in Orion that will be visible for months or even years. But that moment, which could happen tomorrow or in 100,000 years, is not tonight. Tonight, Betelgeuse continues its ancient struggle against gravity, burning through its nuclear fuel reserves, while slowly pulsating with a period of about 400 days. These pulsations cause the star's brightness to vary by nearly a full magnitude as seen from Earth, making Betelgeuse one of the most variable bright stars in our night sky. Chapter 14. Rigel Blue Supergiant Beacon. Voice maintains gentle, hypnotic rhythm. From the red glow of dying Betelgeuse, your journey carries you to its brilliant blue companion in Orion. Rigel, one of the most luminous stars visible to the naked eye from Earth. Located about 860 light-years away, Rigel represents the opposite end of stellar evolution from Betelgeuse, a young, hot, massive star in the prime of its nuclear-burning lifetime. Rigel is actually a complex multiple star system, dominated by a blue supergiant primary star with a mass roughly 20 times that of our Sun. Despite being much less massive than some other known stars, Rigel's extreme surface temperature of about 12,000 Kelvin makes it incredibly luminous, shining with the brightness of roughly 120,000 suns. Most of this energy is emitted in the ultraviolet portion of the spectrum, making Rigel one of the most powerful ultraviolet sources in our local galactic neighborhood. As you approach Rigel, you're immediately struck by its intense blue-white radiance. The star's powerful radiation creates an enormous H2 region, a sphere of ionized hydrogen that extends for dozens of light-years in all directions. Within this region, any hydrogen atoms are quickly ionized by Rigel's intense ultraviolet photons, creating a hot, tenuous plasma that glows faintly in visible light. Rigel's stellar wind is truly impressive, carrying away mass at a rate roughly 10 million times faster than our sun's solar wind. This wind moves at speeds exceeding 2,000 kilometers per second, fast enough to travel from Earth to the Moon in less than 3 minutes. The wind carries away about 1 Earth mass of material every million years, gradually reducing the star's mass over its lifetime. The star rotates rapidly, completing one rotation in less than 2 days. This rapid rotation, combined with the star's powerful stellar wind, creates complex structures in the surrounding interstellar medium. As you float through the region around Rigel, you encounter shockwaves, wind-blown bubbles, and other phenomena created by the interaction between the star's wind and the surrounding gas and dust. Rigel is relatively young by stellar standards, with an estimated age of only 7 to 9 million years. Despite its youth, the star is already showing signs of evolution away from the main sequence. Its core temperature and pressure have increased to the point where it's beginning to burn helium alongside hydrogen, a sign that it's entering the later phases of its stellar lifetime. What time is it now where you're listening? Has the night wrapped itself around you like a cosmic blanket as we've journeyed from star to star? Are you feeling that deep, peaceful relaxation that comes from contemplating the vastness of space and time? Pause for 3 seconds. Perfect. Let that serenity flow through you like starlight. Despite its current brightness and apparent stability, Rigel's future is already written in the stars. With such a large mass, the star will burn through its nuclear fuel reserves relatively quickly. Within the next few million years, Rigel will evolve into a red supergiant similar to Betelgeuse, then end its life in a spectacular supernova explosion that will briefly outshine all the other stars in Orion combined. The explosion will scatter Rigel's outer layers, enriched with heavy elements forged in the star's nuclear furnace, across dozens of light-years of space. This material will eventually be incorporated into new generations of stars and planets, continuing the cosmic cycle of stellar death and rebirth that has shaped our galaxy for billions of years. Chapter 15. The Rosette Nebula Cosmic Flower. Voice becomes more lyrical and flowing. Your peaceful journey through the Orion Arm now brings you to one of the most beautiful star-forming regions in our galaxy. The Rosette Nebula, also known as NGC 2237, located about 5,200 light-years from Earth in the constellation Monoceros. This spectacular emission nebula resembles a cosmic rose blooming in the depths of space. The Rosette Nebula spans approximately 130 light-years in diameter, making it roughly 5 times larger than the famous Orion Nebula. At its heart lies NGC 2244, an open star cluster containing several dozen hot, massive O and B-type stars that were born from the nebula's gas and dust approximately 4 million years ago. These young stellar giants now illuminate and shape their birth cloud with intense ultraviolet radiation and powerful stellar winds. As you float into the Rosette Nebula, you're surrounded by glowing hydrogen gas that creates the nebula's characteristic red coloration. The central cavity of the nebula, that dark hole in the center that gives it the appearance of a flower, has been carved out by the combined stellar winds and radiation pressure from the central star cluster. This process, called stellar feedback, has blown away most of the original molecular cloud material from the central region, creating a hot, low-density bubble surrounded by dense walls of compressed gas and dust. The structure of the Rosette Nebula is incredibly complex, with intricate filaments, globules, and pillars of dense material sculpted by the interplay between stellar radiation, magnetic fields, and turbulent gas motions. Some of these structures are several light-years long, towering pillars of gas and dust that point toward the central star cluster like cosmic fingers reaching across the void. Within these dense structures, new stars are currently forming as gravity overcomes the outward pressure of radiation and stellar winds. You drift past several small, dark globules, Bach globules, where the earliest stages of star formation are taking place. These dense knots of material are slowly contracting under their own gravity, heating up as gravitational potential energy is converted to thermal energy. The temperature structure within the Rosette Nebula is fascinating and complex. The central cavity, heated by the intense radiation from the central stars, reaches temperatures of 10,000 Kelvin or more. But within the dense walls surrounding this cavity, temperatures drop to only a few hundred Kelvin, and deep within the Bach globules, temperatures can be as low as 10 Kelvin above absolute zero. This temperature gradient creates a complex chemistry within the nebula. In the hot, ionized regions, atoms are stripped of their electrons and exist as plasma. In the cooler, denser regions, atoms can combine to form molecules, including water, carbon monoxide, ammonia, and complex organic compounds that may serve as the building blocks for life. How are you feeling as we drift through this cosmic garden? Can you sense the incredible beauty and complexity of stellar birth playing out around us? Let the gentle glow of the nebula fill you with peaceful wonder. Pause for 3 seconds. As you continue floating through the Rosette Nebula, you encounter several elephant trunk structures, dense pillars of gas and dust that are being eroded by the intense radiation from nearby hot stars. These structures get their name from their resemblance to elephant trunks, with dense heads and long, trailing tails that point away from the ionizing stars. At the tips of some of these elephant trunks, small, dense globules are being compressed by the surrounding ionization fronts, potentially triggering new episodes of star formation. This process, known as triggered star formation, may be responsible for creating multiple generations of stars within the nebula, as each generation of massive stars influences the formation of the next. Chapter 16. The Cone Nebula Stellar Sculpture. Voice maintains dreamy, contemplative quality. From the rose-like beauty of the Rosette Nebula, your cosmic journey carries you to another spectacular star-forming region. The Cone Nebula, part of the larger NGC 2264 region in the constellation Monoceros, located about 2,700 light-years from Earth. This distinctive nebula gets its name from the prominent cone-shaped pillar of dense gas and dust that dominates its structure. The Cone Nebula is part of a larger star-forming complex that includes the Christmas Tree Cluster and the Phosphor Nebula, all illuminated by the hot, young stars that have recently formed from the region's molecular cloud material. The entire complex spans about 20 light-years and contains several hundred newly formed stars, most of them less than a few million years old. As you approach the famous cone-shaped structure, you're struck by its imposing presence. The cone extends for about 7 light-years, roughly 1.5 times the distance from our Sun to Proxima Centauri. This enormous pillar is composed of dense molecular gas and dust that has been sculpted by the intense ultraviolet radiation and stellar winds from nearby hot stars, particularly S Monocerotis, a bright O-type star located just outside the field of view of most images of the nebula. The tip of the cone points directly away from S Monocerotis, shaped by the pressure of photons and charged particles streaming from this massive star. The cone structure is incredibly detailed, with intricate filaments and knots of material creating a complex tapestry of light and shadow. The surface of the cone that faces the illuminating star glows faintly as hydrogen molecules are dissociated and ionized by the intense radiation. As you float along the length of the cone nebula, you encounter several Herbig-Haro objects, narrow jets of gas ejected by newly forming stars embedded within the dense molecular material. These jets move at hundreds of kilometers per second, creating shock waves where they collide with the surrounding interstellar medium. The shock-heated gas glows in characteristic emission lines, creating bright knots and filaments that trace the paths of these stellar outflows. Within the dense material of the cone, star formation is actively occurring. Young stellar objects, still embedded in their natal cocoons of gas and dust, are gradually clearing out cavities around themselves through their stellar winds and radiation. Some of these protostars are surrounded by circumstellar disks, the raw material from which planetary systems form. The Cone Nebula region also contains several beautiful reflection nebulae, where starlight from young, hot stars is scattered by dust grains in the surrounding interstellar medium. These nebulae appear blue because small dust grains scatter blue light more efficiently than red light, the same physical process that makes Earth's sky appear blue. Are you finding yourself completely relaxed as we explore these cosmic sculptures together? Has your breathing naturally slowed and deepened as we've drifted from nebula to nebula? Take a moment to appreciate how peaceful and weightless you feel in this cosmic meditation. Wonderful. Let that sense of cosmic peace permeate your entire being. The chemistry within the Cone Nebula is incredibly rich and complex. In the dense, shielded regions where starlight cannot penetrate, molecules can survive and even form complex organic compounds. Observations have detected over 100 different molecular species in similar regions, including water, methanol, formaldehyde, and even amino acids, the building blocks of proteins. The magnetic field structure within the nebula plays a crucial role in star formation, channeling the collapse of gas clouds and influencing the orientation of stellar outflows. As you float through these invisible magnetic field lines, you're moving along the same paths that guide the formation of new stars and planetary systems. Chapter 17. The Eagle Nebula Pillars of Creation. Voice fills with awe while maintaining hypnotic quality. Your journey through the star-forming regions of the Orion Arm now brings you to one of the most famous and spectacular sights in the entire galaxy. The Eagle Nebula, home to the iconic Pillars of Creation. Located about 7,000 light-years from Earth in the constellation Serpens, this magnificent emission nebula showcases star formation in all its dramatic glory. The Eagle Nebula, also catalogued as Messier 16, spans approximately 70 by 55 light-years and contains the young open star cluster NGC 6611. This cluster formed about 5.5 million years ago from the nebula's molecular cloud material and now illuminates and sculpts the surrounding gas and dust with intense ultraviolet radiation and powerful stellar winds. As you approach the famous Pillars of Creation, you're overwhelmed by their sheer scale and majesty. These towering columns of dense gas and dust stretch for 4 to 5 light-years, roughly the distance from our Sun to Proxima Centauri. The pillars are being carved by photoevaporation, as intense ultraviolet radiation from nearby hot stars gradually erodes their surfaces, creating the distinctive elephant trunk shapes that have captivated astronomers and the public alike. The pillars point toward the cluster of hot, massive stars that are sculpting them, like cosmic weather vanes indicating the direction of the stellar radiation. At the tips and along the sides of the pillars, you can see small, dense knots called EGGs, evaporating gaseous globules, where star formation may be occurring. These globules are being compressed by the surrounding ionization fronts, potentially triggering the collapse that leads to new star birth. As you float between the towering pillars, you're surrounded by a complex tapestry of light and shadow. The surfaces of the pillars facing the ionizing stars glow with a faint red light as hydrogen atoms are excited and then emit photons, while the interior regions remain dark and cold, shielded from the intense radiation by the dense dust. The environment within the Eagle Nebula is incredibly dynamic. Stellar winds from the hot cluster stars create expanding bubbles and shock waves that sweep through the nebula at speeds of hundreds of kilometers per second. These shock waves compress the surrounding gas and dust, potentially triggering new episodes of star formation in a process called sequential star formation. Deep within the densest parts of the pillars, where your journey now takes you, temperatures drop to only 10 to 20 Kelvin above absolute zero. Here, in these cosmic refrigerators, simple molecules can stick to dust grains and undergo chemical reactions that create increasingly complex organic compounds. Water ice, methanol, and even amino acids have been detected in similar regions, suggesting that the chemical ingredients for life may be widespread throughout star-forming regions. The magnetic field structure within the Eagle Nebula is complex and highly organized, channeling the flow of ionized gas and influencing the shapes of the pillars and other structures. As you drift along these invisible magnetic field lines, you're following the same paths that guide the formation of new stars and the evolution of the nebula itself. What's remarkable about the pillars of creation is that they may already be gone. The intense radiation from the nearby hot stars has been gradually destroying them, and some estimates suggest that they were completely photoevaporated about 6,000 years ago. Because of the finite speed of light, we're still seeing them as they existed 7,000 years ago, when the light currently reaching Earth began its journey across the galaxy. Where are you listening from tonight, fellow cosmic traveler? Are you nestled comfortably in bed, allowing these stellar vistas to carry you toward peaceful sleep? Can you feel how your body has naturally relaxed as we've journeyed together through these magnificent nebulae? Pause for 3 seconds. Perfect. Let the grandeur of cosmic creation fill you with serene wonder. Chapter 18. The Crab Nebula Stellar Aftermath. Voice becomes more contemplative, reflecting on cosmic cycles. Your peaceful journey through the star-forming regions of our galaxy now brings you to witness the aftermath of stellar death. The Crab Nebula, also known as Messier 1, located about 6,500 light-years from Earth in the constellation Taurus. This spectacular supernova remnant represents the explosive end of a massive star's life, an event that was witnessed and recorded by Chinese astronomers in 1054 CE. As you approach the Crab Nebula, you're struck by its distinctive oval shape and complex internal structure. The nebula spans about 11 light-years in diameter and is expanding outward at roughly 1,500 kilometers per second, fast enough to travel from Earth to the Moon in less than 5 minutes. This expansion has been continuing for nearly 1,000 years since the original supernova explosion, and it will continue for thousands of years to come. At the heart of the nebula lies the Crab Pulsar, the ultradense neutron star remnant of the original massive star. This cosmic lighthouse spins 30 times per second, beaming radiation across the electromagnetic spectrum with each rotation. The pulsar is only about 20 kilometers in diameter but contains more mass than our Sun, creating a gravitational field so intense that the escape velocity from its surface is about 1/3 the speed of light. As you float through the expanding shell of the Crab Nebula, you're surrounded by material that was once deep within the core of a massive star. This stellar debris has been enriched with heavy elements forged in the nuclear furnace of the dying star and during the supernova explosion itself. You encounter atoms of carbon, oxygen, silicon, and iron elements that are essential for the formation of rocky planets and the complex chemistry of life. The nebula glows with 2 distinct types of emission. The reddish filamentary structure is created by hydrogen and other light elements that have been ionized by the intense radiation environment within the nebula. These filaments trace the shock waves and magnetic field structures that permeate the expanding shell, creating a complex web of glowing gas that extends throughout the nebula. The bluish-white glow that fills the interior of the nebula is synchrotron radiation, produced by high-energy electrons spiraling around magnetic field lines at nearly the speed of light. This emission comes from the pulsar wind nebula, a region where the spinning neutron star's magnetic field accelerates particles to incredible energies and flings them outward into the surrounding space. The Crab pulsar is one of the most precisely studied objects in astronomy, its regular pulse serving as a cosmic clock accurate to within microseconds. The pulsar's rotation is gradually slowing down as it loses energy through radiation and particle acceleration, providing astronomers with detailed insights into the physics of these exotic objects. As you continue floating through the nebula, you encounter shock waves where the expanding supernova ejecta collides with the surrounding interstellar medium. These shocks heat the gas to millions of degrees, creating conditions where complex nuclear reactions can occur and where cosmic rays, high-energy particles that permeate our galaxy, are accelerated to tremendous energies. The Crab Nebula represents a crucial link in the cosmic recycling process that has shaped our galaxy for billions of years. The heavy elements dispersed by this and countless other supernovae have enriched the interstellar medium, providing the raw materials from which new generations of stars and planets can form. The calcium in your bones, the iron in your blood, and the oxygen you breathe were all forged in the nuclear furnaces of massive stars and dispersed by supernova explosions like the one that created the Crab Nebula. Are you feeling that deep sense of cosmic connection as we explore this stellar graveyard? Can you sense how you're intimately connected to these cosmic processes? How the atoms in your body were once part of ancient stars? Let that profound realization bring you peace and wonder. Pause for 3 seconds. Chapter 19, The Ring Nebula Planetary Nebula Gem. Voice becomes gentler, more intimate. From the violent aftermath of a supernova, your cosmic journey now takes you to witness a gentler form of stellar death. The Ring Nebula, also known as Messier 57, located about 2,300 light-years away in the constellation Lyra. This beautiful planetary nebula represents the final chapter in the life of a star similar to our Sun. Despite its name, the Ring Nebula has nothing to do with planets. Early astronomers called these objects planetary nebulae because their round, disc-like appearance resembled the planets Uranus and Neptune when viewed through small telescopes. In reality, planetary nebulae are the expelled outer layers of dying stars, illuminated by the hot white dwarf remnants at their centers. As you approach the Ring Nebula, you're struck by its perfect symmetry and delicate beauty. The nebula appears as a nearly perfect ring when viewed from Earth, but as your cosmic perspective allows you to see it in 3 dimensions, you realize it's actually more like a barrel or cylinder oriented with its axis pointing almost directly toward our solar system. The Ring Nebula spans about 1 light-year in diameter, roughly 1/4 the distance from our Sun to Proxima Centauri. At its center glows a tiny white dwarf star with a surface temperature of about 120,000 Kelvin, making it one of the hottest known white dwarf stars. This stellar remnant contains roughly 60% of our Sun's mass compressed into a sphere about the size of Earth. The beautiful colors of the Ring Nebula tell the story of its composition and structure. The red outer regions are dominated by hydrogen emission, while the blue-green center is rich in ionized helium and oxygen. These colors are created as the intense ultraviolet radiation from the central white dwarf ionizes different elements at different distances from the star, creating a cosmic rainbow that reveals the nebula's chemical composition. As you float through the expanding shell of the Ring Nebula, you're surrounded by material that was once part of the outer atmosphere of a red giant star. About 20,000 years ago, this star expelled its outer layers in a series of gentle pulsations, creating the beautiful shell structure we see today. The material is expanding outward at about 20 kilometers per second, much slower than the violent expansion of supernova remnants like the Crab Nebula. The structure of the Ring Nebula is more complex than its simple appearance might suggest. High-resolution observations reveal intricate knots, filaments, and density variations throughout the nebula, created by instabilities in the original stellar atmosphere and interactions with the surrounding interstellar medium. The nebula also shows a faint outer halo, material expelled during earlier phases of the star's evolution. Within the nebula, you encounter a fascinating variety of ionization zones. Close to the central white dwarf, the intense ultraviolet radiation strips electrons from even the heaviest elements, creating a region of highly ionized plasma. Farther out, where the radiation is less intense, atoms can retain more of their electrons, creating the different emission zones that give the nebula its characteristic colors. The Ring Nebula provides a preview of our Sun's distant future. In about 5 billion years, our Sun will exhaust the hydrogen fuel in its core and begin to evolve into a red giant star. During this phase, it will expand to roughly the size of Earth's orbit, engulfing Mercury and Venus and making Earth uninhabitable. Eventually, the Sun will begin to pulsate and expel its outer layers, creating a planetary nebula similar to the Ring Nebula, with a white dwarf remnant at its center. How does it feel to contemplate our Sun's distant future as we float through this cosmic preview? Are you finding comfort in the vast timescales involved, the billions of years that stretch between now and that distant transformation? Let the gentle beauty of the Ring Nebula fill you with peaceful acceptance of cosmic cycles. Pause for 3 seconds. The white dwarf at the center of the Ring Nebula will continue to cool and fade over billions of years, eventually becoming a cold, dark cinder floating through space. But the beautiful nebula surrounding it will gradually expand and fade, its material mixing with the interstellar medium and potentially being incorporated into new generations of stars and planets. This is the gentle way that stars like our Sun return their enriched material to the galaxy, contributing to the cosmic recycling process that has created the chemical diversity we see around us today. Chapter 20. The Cat's Eye Nebula Cosmic Complexity. Voice maintains gentle, dreamy quality while conveying wonder. Your journey through the stellar afterlives continues as you drift toward one of the most complex and beautiful planetary nebulae in our galaxy. The Cat's Eye Nebula, also known as NGC 6543, located about 3,300 light-years away in the constellation Draco. This intricate nebula showcases the incredible complexity that can arise during the final stages of stellar evolution. The Cat's Eye Nebula is named for its distinctive appearance, which resembles the iris of a cat's eye when viewed through telescopes. But as you approach this cosmic artwork, you begin to appreciate the incredible three-dimensional structure that creates this illusion. The nebula consists of multiple concentric shells, braided helical structures, and jet-like features that extend far beyond the bright central region. At the heart of the nebula lies an O-type central star, one of the hottest known central stars of any planetary nebula. With a surface temperature exceeding 80,000 Kelvin, this white dwarf remnant floods the surrounding material with intense ultraviolet radiation, ionizing the expelled stellar atmosphere and causing it to glow in the beautiful colors we observe. As you float through the Cat's Eye Nebula, you're surrounded by one of the most complex structures ever observed in a planetary nebula. The bright central region contains intricate knots and filaments, while farther out, you encounter a series of concentric shells that were expelled during different episodes of the original star's evolution. These shells are separated by regions of lower density, creating a layered structure that resembles the rings of an onion. The most remarkable features of the Cat's Eye Nebula are the symmetrical jets and ANSI handles that extend from the central region. These structures suggest that the original star may have been part of a binary system, with gravitational interactions between the two stars creating the complex magnetic field structures that shaped the nebula's evolution. The presence of a companion star could explain the intricate braided structures and the precise symmetry observed throughout the nebula. The nebula's spectrum reveals a rich chemistry, with emission lines from hydrogen, helium, nitrogen, oxygen, and other elements created through nucleosynthesis in the original star's interior. The different ionization zones within the nebula create a natural laboratory for studying atomic physics under extreme conditions, with some regions containing plasma hotter than the surface of most stars. One of the most intriguing aspects of the Cat's Eye Nebula is its rapid evolution and structural complexity. The nebula shows evidence of multiple ejection episodes, with material expelled at different velocities and in different directions over a period of several thousand years. This suggests that the death throes of the original star were far from simple, involving complex interactions between stellar pulsations, magnetic fields, and possibly a binary companion. As you continue exploring the nebula's outer regions, you encounter the extensive halo structure that surrounds the bright central nebula. This halo was expelled much earlier in the star's evolution, when it was an asymptotic giant branch star undergoing thermal pulses in its helium-burning shell. The halo material has been expanding for tens of thousands of years and now extends for several light-years around the central nebula. The Cat's Eye Nebula challenges our understanding of how single stars evolve and die. The complex structures observed in this nebula cannot be easily explained by simple models of stellar evolution, suggesting that binary interactions, magnetic fields, and rotation may play crucial roles in shaping the final stages of stellar life. What's your sense of time right now as we explore these cosmic complexities together? Are you finding that the vast timescales of stellar evolution are helping you release the immediate concerns of daily life? Let the intricate beauty of the Cat's Eye Nebula guide you into deeper relaxation. Pause for 3 seconds. The study of planetary nebulae like the Cat's Eye provides crucial insights into the chemical evolution of our galaxy. These nebulae return enriched material to the interstellar medium, material that has been processed through nuclear reactions in stellar cores and exposed to the extreme conditions present during the late stages of stellar evolution. This recycled material becomes part of the next generation of stars and planets, continuing the cosmic cycle that has shaped our galaxy for billions of years. Chapter 21. Approaching Sagittarius A*, the Galactic Center. Voice becomes more profound and mysterious. Your cosmic journey now takes you toward the most massive and mysterious object in our galaxy. Sagittarius A*, the supermassive black hole that lurks at the very center of the Milky Way. Located about 26,000 light-years from Earth, this gravitational monster contains roughly 4 million times the mass of our Sun, all compressed into a region smaller than our solar system. As you drift toward the galactic center, the stellar environment around you becomes increasingly dense and chaotic. This region, known as the galactic bulge, contains some of the oldest stars in our galaxy, ancient red giants and white dwarfs that formed when the Milky Way was young. The density of stars here is millions of times greater than in our solar neighborhood, creating a stellar metropolis unlike anything in the spiral arms. The journey towards Sagittarius A*, takes you through increasingly exotic environments. You pass through vast molecular clouds heated by the intense radiation field near the galactic center, regions where the temperature can reach several hundred Kelvin even in the densest, most shielded areas. These clouds contain complex organic molecules, including alcohols and amino acids, synthesized in the harsh radiation environment near the galaxy's heart. As you approach within a few light-years of Sagittarius A*, you encounter the circumnuclear disk, a ring of dense molecular gas and dust that orbits the central black hole. This disk contains about 100,000 times the mass of our Sun and serves as a reservoir of material that occasionally feeds the black hole, causing it to flare with increased activity. The gravitational field of Sagittarius A*, dominates the local environment, creating a region where the laws of physics as we normally experience them are pushed to their limits. Within the innermost stable circular orbit, about 120 times the Schwarzschild radius of the black hole, no stable orbits are possible, and any material that ventures this close is doomed to spiral inward and disappear beyond the event horizon. You observe several dozen massive stars orbiting close to Sagittarius A*, their elliptical paths carrying them to within a few light hours of the black hole's event horizon. These stars, known as the S-stars, provide some of the best evidence for the black hole's existence and have been used to test Einstein's theory of general relativity under extreme gravitational conditions. One of these stars, S2, follows a highly elliptical orbit that brings it within 120 astronomical units of the black hole every 16 years. During its closest approach in 2018, this star reached speeds of over 7,600 kilometers per second, about 2.5% of the speed of light, and experienced gravitational redshift and relativistic precession effects predicted by Einstein's theory. As you float in this extreme environment, you witness occasional flares from Sagittarius A*, as small amounts of material fall into the black hole. These flares can increase the black hole's luminosity by factors of hundreds or thousands, creating brief but intense bursts of X-ray and infrared radiation that illuminate the surrounding region. The space around Sagittarius A* is filled with high-energy particles and intense magnetic fields that create one of the most extreme environments in our galaxy. Cosmic rays are accelerated to incredible energies, and the magnetic field strength can exceed 100 times that found in typical interstellar space. Are you feeling the profound weight of this cosmic center as we approach it together? Can you sense the incredible gravitational forces at work here, the way space and time themselves are warped by the presence of this massive object? Let the mystery and power of the galactic center fill you with awe and wonder. Pause for 3 seconds. Despite its fearsome reputation, Sagittarius A* is currently in a relatively quiet state, accreting material at a very low rate compared to active galactic nuclei in other galaxies. The black hole is essentially starving, with most of the material in its vicinity being ejected rather than consumed. This quiescent state has persisted for thousands of years, though evidence suggests that Sagittarius A* was much more active in the past. Chapter 22. The Sagittarius Arm Spiral Architecture. Voice becomes more expansive, describing grand structures. From the intense gravitational environment near the galactic center, your cosmic journey now carries you outward toward one of the Milky Way's major spiral arms. The Sagittarius Arm, also known as the Sagittarius-Carina Arm. This magnificent structure represents one of the galaxy's primary spiral features, a grand design pattern that has persisted for hundreds of millions of years. As you float outward from the galactic center, you begin to appreciate the true scale and beauty of our galaxy's spiral structure. The Sagittarius Arm is a density wave, a region where stars, gas, and dust are compressed by gravitational forces, creating the bright, star-forming regions that trace out the spiral pattern. This arm extends for thousands of light years, curving gracefully around the galaxy like a cosmic pinwheel. The spiral arms are not rigid structures, but rather waves of compression that rotate around the galactic center at a different speed than the stars themselves. Individual stars drift in and out of the spiral arms over millions of years, but the density wave pattern persists, maintained by gravitational resonances and feedback from star formation processes. As you float through the Sagittarius Arm, you encounter a rich tapestry of stellar populations and interstellar phenomena. The arm contains numerous H2 regions, vast clouds of ionized hydrogen surrounding clusters of hot, young stars. These regions appear as bright red patches scattered along the arm, each one a stellar nursery where new stars are being born from the compressed gas and dust of the spiral density wave. The Sagittarius Arm is home to several spectacular star-forming regions, including the Lagoon Nebula, the Trifid Nebula, and the Eagle Nebula that you visited earlier in your journey. These nebulae represent active star formation sites where the compression from the spiral density wave has triggered the gravitational collapse of molecular clouds, leading to the birth of new stellar systems. Between the bright star-forming regions, you drift through vast expanses of interstellar medium, the thin soup of gas and dust that fills the space between stars. Even this seemingly empty space is shaped by the spiral structure, with magnetic fields, cosmic rays, and turbulent motions all influenced by the galaxy's grand design pattern. The stellar populations within the Sagittarius Arm reflect its role as an active star-forming region. Young, hot O and B-type stars dominate the most prominent features, their intense ultraviolet radiation ionizing the surrounding gas and creating the bright emission nebulae that make spiral arms visible in other galaxies. These massive stars have short lifetimes and will explode as supernovae within a few million years, enriching the interstellar medium with heavy elements and triggering new rounds of star formation. Mixed in with these stellar youngsters are older populations of stars that formed during previous passages through spiral arms. The Sun itself has likely passed through several spiral arms during its 4.6 billion-year journey around the galaxy, each passage potentially influencing the evolution of life on Earth through increased cosmic ray exposure and climate changes. As you continue your peaceful drift through the Sagittarius Arm, you encounter the gravitational influence of the spiral density wave itself. This wave is thought to be maintained by a combination of factors, including gravitational resonances with the galaxy's central bar structure, feedback from star formation and supernova explosions, and the overall rotation pattern of the galaxy. The magnetic field structure within the spiral arm is complex and highly organized, following the spiral pattern and channeling the flow of cosmic rays and charged particles. These magnetic fields play crucial roles in star formation, helping to support molecular clouds against gravitational collapse, while also facilitating the compression that eventually leads to stellar birth. Where are you right now as we explore these grand galactic structures together? Are you comfortably settled in for the night, letting the vast scales of space and time carry you toward peaceful sleep? Can you feel how your breathing has naturally synchronized with the gentle rhythm of our cosmic journey? Pause for 3 seconds. Perfect. Let the majesty of spiral structure wash over you like a gentle galactic tide. Chapter 23. The Perseus Arm Stellar Highway. Voice maintains gentle, hypnotic quality while describing grand vistas. Your journey through the Milky Way's spiral architecture now carries you toward another major structural feature. The Perseus Arm, one of the galaxy's most prominent spiral arms and home to some of the most spectacular star-forming regions in our cosmic neighborhood. Located on the opposite side of our solar system from the galactic center, the Perseus Arm represents a stellar highway stretching across thousands of light years. As you approach the Perseus Arm, you notice how the stellar density increases dramatically. This arm contains roughly twice as many stars per unit volume as the interarm regions, creating a brilliant river of light that would be clearly visible if you could view the Milky Way from outside. The increased stellar density is accompanied by enhanced concentrations of gas and dust, the raw materials from which new stars continue to form. The Perseus Arm is home to the famous double cluster in Perseus, also known as NGC 869 and NGC 884. As you float into this region, you're surrounded by over 300 hot, young stars that formed from the same molecular cloud roughly 12 to 15 million years ago. These stellar siblings shine with combined luminosity thousands of times greater than our Sun, creating a brilliant beacon that's visible to the naked eye from Earth despite being over 7,000 light-years away. The two clusters of the double cluster are separated by only a few hundred light-years and are moving through space together, though they will eventually drift apart as galactic tidal forces gradually disrupt their gravitational binding. For now, they create one of the most spectacular sights in the northern winter sky, a cosmic jewelry box of blue and white giant stars set against the backdrop of the Milky Way. As you drift deeper into the Perseus Arm, you encounter the California Nebula, a vast emission nebula that spans over 100 light-years in length. This enormous structure is illuminated by Persei, a hot blue giant star whose intense ultraviolet radiation ionizes the surrounding hydrogen gas, causing it to glow with the characteristic red color of hydrogen alpha emission. The nebula's distinctive shape, which resembles the outline of the state of California, is sculpted by stellar winds and radiation pressure from Persei and other nearby hot stars. The interstellar medium within the Perseus Arm shows clear signs of the spiral density wave's influence. Molecular clouds are compressed and heated by the passage through the spiral shock, triggering episodes of star formation that propagate along the arm like a slow-motion cosmic fireworks display. This process, known as stochastic self-propagating star formation, helps maintain the spiral structure over geological timescales. You float past several massive molecular cloud complexes, each containing enough material to form thousands of stars like our Sun. These clouds show a hierarchical structure, with dense cores embedded within larger clumps, which are themselves contained within even larger cloud complexes. This fractal-like organization reflects the turbulent nature of the interstellar medium and the complex interplay between gravity, magnetic fields, and stellar feedback. The Perseus Arm also contains several notable supernova remnants, the expanding shells of gas and dust created by the explosive deaths of massive stars. These remnants play crucial roles in the ecology of the spiral arm, heating and stirring the interstellar medium, accelerating cosmic rays to high energies, and dispersing heavy elements forged in stellar cores throughout the local environment. One particularly interesting feature of the Perseus Arm is the presence of several runaway stars, massive stars that have been ejected from their birth clusters at high velocities. These stellar refugees create bow shocks as they plow through the interstellar medium at speeds of tens of kilometers per second, leaving behind trails of heated and compressed gas that can stretch for several light-years. Are you feeling that deep sense of cosmic scale as we drift through these stellar highways? Can you appreciate how our own solar system fits into this grand galactic architecture? How we're part of this magnificent spiral dance that has been continuing for billions of years? Pause for 3 seconds. Let that perspective bring you peace and wonder as we continue our gentle journey. The magnetic field structure within the Perseus Arm is particularly well organized, with field lines that generally follow the spiral pattern but show complex variations on smaller scales. These magnetic fields channel the flow of cosmic rays and help regulate star formation by providing additional pressure support against gravitational collapse in some regions while enhancing compression in others. The Perseus Arm represents a dynamic, evolving structure that changes on timescales ranging from millions to hundreds of millions of years. The spiral density wave that maintains the arm's structure rotates at a different angular velocity than the stars themselves, creating a pattern that persists even as individual stars and gas clouds drift in and out of the arm over cosmic time. Chapter 24: The Outer Spiral Arm's Galactic Frontiers. Voice becomes more contemplative and peaceful. As your cosmic journey carries you further from the galactic center, you begin to explore the outer regions of the Milky Way, where the galaxy's spiral structure becomes more tenuous and the stellar density drops significantly. These outer spiral arms, extensions of the major arms that wrap around the galaxy multiple times, represent the frontiers of our galactic home, regions where the gravitational influence of the central bulge weakens and the galaxy gradually fades into the intergalactic void. The outer arms contain a fascinating mix of stellar populations. While the massive, short-lived stars that dominate the inner spiral arms are less common here, you still encounter active star-forming regions, though they are smaller and more widely scattered. The lower metallicity in these outer regions, a consequence of less efficient mixing of heavy elements from the galactic center, creates slightly different conditions for star and planet formation. As you float through these outer regions, you encounter several extended HI regions, vast clouds of neutral hydrogen that have not yet been ionized by nearby hot stars. These clouds can span hundreds of light-years and contain masses equivalent to millions of suns, representing enormous reservoirs of star-forming material that will fuel stellar birth for billions of years to come. The gravitational field in the outer galaxy is dominated by dark matter, that mysterious substance that makes up roughly 85% of all matter in the universe but interacts only through gravity. As you drift through these regions, you're actually moving through a vast dark matter halo that extends far beyond the visible disk of the galaxy, creating the gravitational scaffolding that holds the entire Milky Way together. The rotation curve of the galaxy, the relationship between orbital velocity and distance from the galactic center, provides some of the strongest evidence for dark matter's existence. In the outer regions where you're now traveling, stars and gas clouds orbit the galactic center at speeds that would cause them to fly off into intergalactic space if only the gravity of visible matter were present. The additional gravitational influence of dark matter is required to explain the observed orbital velocities. The outer spiral arms also contain some of the galaxy's most isolated stellar populations. Globular clusters, ancient spherical collections of hundreds of thousands of old stars, orbit through these regions on highly elliptical paths that carry them far from the galactic plane. These stellar cities formed early in the galaxy's history and serve as fossils of the Milky Way's youth, preserving information about conditions during the first billion years of galactic evolution. As you continue outward, you encounter the galaxy's thick disk population, older stars with higher orbital inclinations that create a puffy, extended component of the galactic disk. These stars formed during a more chaotic period in the galaxy's history, when mergers with smaller satellite galaxies stirred up the stellar populations and heated the disk structure. The interstellar medium in the outer galaxy is significantly different from the inner regions. The lower stellar density means less heating from stellar radiation and fewer supernova explosions, creating cooler, more quiescent conditions. The magnetic field strength is also lower, and cosmic ray densities are reduced, creating an environment that may be more favorable for the long-term stability of planetary atmospheres. How are you feeling as we explore these quiet galactic outskirts together? Are you finding peace in the vastness and solitude of these outer regions? Take a moment to notice how completely relaxed your body has become during our cosmic journey. Pause for 3 seconds. Wonderful. Let the gentle emptiness of the outer galaxy cradle you in cosmic peace. The outer edges of the Milky Way are also where we encounter evidence of the galaxy's violent past. Stellar streams, elongated trails of stars torn from disrupted satellite galaxies, wind through these regions like cosmic rivers, tracing the gravitational carnage of galactic interactions that occurred billions of years ago. These streams are gradually being dispersed and absorbed into the galaxy's general stellar population, but they preserve evidence of the Milky Way's growth through merger and accretion. The most famous of these disrupted satellites is the Sagittarius dwarf elliptical galaxy, which is currently being torn apart by the Milky Way's tidal forces. Streams of stars from this dying galaxy wrap around the Milky Way multiple times, creating some of the most extensive stellar structures in our galactic neighborhood. Chapter 25. The Galactic Halo Ancient Guardians. Voice becomes more mystical and profound. Beyond the visible disk of the Milky Way, your journey now takes you into the galactic halo, a vast spherical region that extends hundreds of thousands of light-years from the galactic center. This is the realm of the galaxy's oldest stellar populations, ancient guardians that have witnessed the entire history of the Milky Way's evolution from a chaotic collection of merging protogalaxies to the magnificent spiral structure we see today. The galactic halo is a sparse, lonely place. The stellar density here is thousands of times lower than in the galactic disk, with vast gulfs of nearly empty space separating individual stars and stellar systems. Yet despite its emptiness, the halo contains some of the most fascinating and important objects in our galaxy, including globular clusters, ancient field stars, and the invisible dark matter that dominates the galaxy's mass. As you float through the inner halo regions, you encounter your first globular cluster, M13, the Great Cluster in Hercules. This ancient stellar city contains over 300,000 stars packed into a sphere only about 145 light-years in diameter. The stars in M13 are incredibly old, nearly as old as the universe itself, with ages estimated at 11.65 billion years. The core of M13 is so dense that stars are separated by only light weeks rather than the light-years typical of our solar neighborhood. In such a crowded environment, close encounters between stars are common, leading to exotic phenomena like blue stragglers, old stars that appear young because they've been rejuvenated by stellar collisions or mass transfer from companions. As you drift deeper into the cluster, you witness the complex gravitational dance of hundreds of thousands of ancient suns. The cluster center contains several X-ray sources, likely neutron stars or black holes that are accreting material from nearby companions. These compact objects represent the final evolutionary states of the cluster's most massive original members, which long ago exhausted their nuclear fuel and collapsed into exotic stellar remnants. The globular cluster system of the Milky Way contains over 150 known clusters, each one a fossil from the galaxy's early history. These clusters formed during the first few billion years after the Big Bang, when the universe was much smaller and denser, and conditions were ripe for the formation of these massive stellar aggregates. The chemical composition of globular cluster stars tells the story of the early universe. These ancient suns contain very low abundances of heavy elements, what astronomers call metals, reflecting the fact that they formed before generations of massive stars had time to synthesize and disperse significant quantities of carbon, oxygen, silicon, and iron into the interstellar medium. As you continue your journey through the halo, you encounter isolated field stars that are even older than those in globular clusters. Some of these ancient suns are among the oldest objects in the universe, formed less than 1 billion years after the Big Bang. Their spectra reveal the chemical signatures of the first generation of stars, providing crucial insights into the earliest epochs of cosmic history. The halo is also home to several stellar streams, the tidally disrupted remains of satellite galaxies and globular clusters that have been torn apart by the Milky Way's gravitational field. These streams wrap around the galaxy like cosmic spaghetti, tracing the orbital paths of their progenitor objects and providing evidence for the hierarchical assembly of our galaxy through mergers and accretion. One of the most prominent of these streams is associated with the Sagittarius dwarf elliptical galaxy, which is currently being cannibalized by the Milky Way. The stream from this disrupted galaxy wraps around our galaxy multiple times, creating an extended structure that spans much of the sky as seen from Earth. Are you feeling the profound age and wisdom of these ancient stellar populations? Can you sense the incredible span of cosmic history represented by these halo objects, the billions of years they've been silently orbiting our galaxy? Let their ancient presence bring you deep peace and perspective. Pause for 3 seconds. The dark matter halo that surrounds the Milky Way is thought to extend even further than the stellar halo, possibly reaching distances of over 1 million light-years from the galactic center. This invisible component contains roughly 10 times more mass than all the stars, gas, and dust in the galaxy combined, creating the gravitational framework that determines the galaxy's structure and evolution. Within this dark matter halo, substructure abounds. Numerical simulations predict that the halo should contain thousands of smaller dark matter subhalos, some of which may host their own populations of stars in the form of dwarf satellite galaxies. The search for these faint companions is an active area of astronomical research, with new discoveries regularly expanding our understanding of the Milky Way's extended family. Chapter 26. The Local Group, Galactic Neighborhood. Voice expands to encompass even grander scales. As your cosmic journey carries you beyond the boundaries of the Milky Way itself, you enter the realm of the local group, the small cluster of galaxies that includes our own Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. This gravitationally bound collection of galaxies spans roughly 10 million light-years and represents our immediate cosmic neighborhood in the vast universe. The local group is dominated by two large spiral galaxies, our own Milky Way and the Andromeda Galaxy, M31, located about 2.5 million light-years away. These two galactic giants contain the vast majority of the mass and luminosity in the local group, with Andromeda being somewhat larger and more massive than the Milky Way. The third largest member, the Triangulum Galaxy, M33, is considerably smaller but still a respectable spiral galaxy with active star formation regions. As you float in the intergalactic space between these galaxies, you're surrounded by an incredibly tenuous medium, far more empty than even the most isolated regions of the galactic halo. The density here is so low that you might encounter only a few hydrogen atoms per cubic meter, creating conditions that approach the perfect vacuum that physicists can only dream of achieving in terrestrial laboratories. Yet even this seemingly empty space is not truly empty. It's filled with dark matter, cosmic rays from distant galaxies, and the faint afterglow of the Big Bang itself. The cosmic microwave background radiation that pervades all of space and provides a fossil record of the universe when it was only 380,000 years old and first became transparent to light. The gravitational dance between the Milky Way and Andromeda dominates the dynamics of the local group. These two galaxies are currently approaching each other at about 110 kilometers per second, and they will eventually collide and merge in approximately 4.5 billion years. This future collision, dubbed Milkomeda by astronomers, will fundamentally reshape the local group and create a giant elliptical galaxy from the merger of two spirals. But that cosmic collision is still billions of years in the future. For now, you float peacefully in the space between galaxies, contemplating the vast scales of distance and time that characterize the universe beyond our galactic home. The nearest large galaxy group, the Virgo cluster, lies about 54 million light-years away, more than 5 times the diameter of the entire local group. Surrounding the major galaxies of the local group is a collection of smaller satellite galaxies and dwarf galaxies. The Milky Way alone has over 50 confirmed satellite galaxies, including the famous Magellanic Clouds visible from the southern hemisphere. These smaller galaxies are gradually being disrupted by tidal forces from their larger neighbors, contributing their stars and dark matter to the growing halos of the major galaxies. The local group as a whole is part of an even larger structure called the local supercluster or Virgo supercluster, a collection of galaxy groups and clusters that spans roughly 110 million light-years. Our local group sits on the outskirts of this supercluster, in a relatively sparse region known as the local void. As you drift through this cosmic neighborhood, you begin to appreciate the hierarchical nature of cosmic structure. Stars are bound into planetary systems exist within galaxies, galaxies are grouped into clusters and superclusters, and these larger structures form an intricate cosmic web of matter separated by vast voids that contain very little visible matter. The expansion of the universe itself becomes apparent at these scales. While the local group is gravitationally bound and not participating in cosmic expansion, more distant galaxy groups and clusters are receding from us due to the expansion of space itself, a phenomenon discovered by Edwin Hubble in the 1920s and now understood to be accelerating due to the mysterious influence of dark energy. What time is it now in your part of the world? Has the night deepened around you as we've journeyed from our solar system to the very edges of our galactic neighborhood? Are you feeling that profound sense of cosmic perspective that comes from contemplating these vast scales of space and time? Pause for 3 seconds. Let the majesty of the local group fill you with wonder and peace as we prepare for the final leg of our cosmic journey. Chapter 27. The Cosmic Web Universal Architecture. Voice becomes profound and all-encompassing. Your journey through the cosmos now reaches its grandest scale as you float beyond the local group into the vast architecture of the universe itself. The cosmic web, a magnificent network of dark matter filaments, galaxy clusters, and enormous voids that spans the entire observable universe. This is the largest scale structure in the cosmos, a pattern that emerged from tiny quantum fluctuations in the early universe and has been growing and evolving for over 13.8 billion years. As you drift outward from the local group, you begin to perceive the true structure of the universe. Galaxies are not randomly scattered through space, but are organized into a vast network that resembles a three-dimensional spider web. Dense filaments of dark matter and galaxies stretch across hundreds of millions of light-years, intersecting at massive galaxy clusters that contain thousands of individual galaxies bound together by gravity. The local group itself sits within one of these cosmic filaments, connected to the larger cosmic web through streams of dark matter and scattered galaxies. As you float along this filament, you encounter other galaxy groups and isolated galaxies, all moving through space according to the gravitational influence of the underlying dark matter distribution. Between the filaments lie enormous voids, vast regions of space that contain very few galaxies and appear almost empty on cosmic scales. These voids can span hundreds of millions of light-years, creating cosmic bubbles in the distribution of matter that give the universe its foam-like structure on the largest scales. Despite their apparent emptiness, these voids play crucial roles in cosmic evolution, providing the low-density regions into which matter flows to create the filamentary structure we observe. The cosmic web is dominated by dark matter, that mysterious substance that makes up roughly 27% of the universe's total mass energy. Dark matter doesn't interact electromagnetically, so it cannot be observed directly, but its gravitational influence shapes the large-scale structure of the cosmos. The visible galaxies and gas clouds we can observe represent only the bright tracers of this underlying dark matter framework. As you float through this cosmic architecture, you encounter massive galaxy clusters, some of the largest gravitationally bound structures in the universe. These clusters can contain thousands of individual galaxies, along with vast quantities of hot, X-ray-emitting gas and enormous reservoirs of dark matter. The largest clusters have masses equivalent to thousands of trillions of suns, creating gravitational fields so strong that they bend the path of light itself, acting as cosmic lenses that can magnify and distort the images of even more distant galaxies. The Virgo cluster, lying about 54 million light-years from the local group, represents the nearest major galaxy cluster and the gravitational center of our local supercluster. This massive collection contains over 1,300 member galaxies, including the giant elliptical galaxy M87, which harbors one of the most massive black holes known to science, with a mass equivalent to 6.5 billion suns. The cosmic web continues to evolve through the ongoing expansion of the universe and the continued growth of structure through gravitational attraction. Dark matter halos merge and grow larger, while galaxy formation and evolution proceed within this cosmic framework. The process is driven by the same fundamental forces that have shaped structure in the universe since the earliest epochs following the Big Bang. On the very largest scales, the universe appears remarkably homogeneous and isotropic. It looks essentially the same in all directions and at all locations. This cosmic principle, supported by observations of the cosmic microwave background and large-scale galaxy surveys, suggests that we do not occupy a special position in the universe, and that the same physical laws apply everywhere. The cosmic web represents the culmination of cosmic evolution from the nearly smooth early universe to the complex, structured cosmos we observe today. This evolution has been driven by the competing influences of gravitational attraction, which tends to clump matter together, and cosmic expansion, which tends to separate structures over time. Are you feeling the overwhelming grandeur of cosmic structure as we reach the largest scales of our universe? Can you sense your connection to this vast cosmic web? How every atom in your body was forged in stellar cores and is now participating in this magnificent cosmic dance? Pause for 3 seconds Let the infinite beauty of the cosmic web embrace you with peace and wonder. Chapter 28. Return to the Orion Arm coming home. Voice becomes warmer and more intimate, like returning home. After journeying to the very edges of cosmic structure, your peaceful voyage now gently carries you back toward home, back to the familiar spiral arm where Earth and our solar system reside. As you drift inward through the cosmic web, past distant galaxy clusters and through the local group, you begin to see the Milky Way growing larger and brighter, welcoming you back to your galactic home. Re-entering the outer regions of our galaxy, you're struck by how familiar everything feels after your cosmic odyssey. The stellar density gradually increases as you move inward through the galactic halo, past ancient globular clusters and stellar streams that now seem like old friends greeting you on your return journey. The dark matter halo that seemed so mysterious during your outward journey now feels like a protective embrace, holding the galaxy together with invisible threads of gravity. As you drift back into the galactic disk, the spiral structure becomes apparent once again. You pass through the outer arms, where star formation proceeds at a gentle pace in the lower density environment, then through the Perseus Arm with its brilliant star clusters and emission nebulae. Each region carries memories of your earlier passage, but now you see them with the expanded perspective gained from your journey to cosmic scales. The Orion Arm comes into view, that modest spiral structure that serves as our cosmic address. Compared to the major arms like Perseus and Sagittarius, the Orion Arm seems small and quiet, but it's home to an incredible diversity of stellar populations and interstellar phenomena. As you drift back into this familiar region, you pass the star-forming regions you visited earlier, the Eagle Nebula, the Orion Nebula, the Rosette Nebula, all still actively creating new stars from the gravitational collapse of molecular clouds. You float past the stellar graveyards where massive stars have ended their lives in spectacular fashion. The Crab Nebula with its spinning pulsar, the expanding shells of ancient supernovae, the beautiful planetary nebulae where sun-like stars have gently expelled their outer layers. These cosmic recycling centers continue their important work of enriching the interstellar medium with heavy elements forged in stellar cores. The individual stars of your stellar neighborhood come back into view. Brilliant Vega with its debris disk, the triple star system of Alpha Centauri, red giant Betelgeuse in its final evolutionary phases, and blue supergiant Rigel blazing with the light of hundreds of thousands of suns. Each star carries its own story of nuclear fusion, stellar evolution, and eventual death, contributing to the grand narrative of galactic chemical evolution. As you drift closer to home, you encounter the Sun, that ordinary G-type star that has provided stable energy output for over 4.5 billion years, enabling the development of complex chemistry and eventually life on the third planet in its system. From your cosmic perspective, gained through this long journey, you can appreciate just how special the stability is, how many factors had to align perfectly to create and maintain conditions suitable for life. The solar system itself comes back into view, with its orderly arrangement of planets, asteroid belts, and cometary reservoirs. You drift past the gas giants, Jupiter with its protective gravitational influence, Saturn with its magnificent rings, distant Uranus and Neptune in their cold, outer orbits. The inner rocky planets appear as tiny specks, yet you know that one of them harbors the only confirmed life in the universe. Earth grows larger as you approach, that pale blue dot suspended in the cosmic dark. From space, there are no national boundaries, no conflicts, no divisions, just a single, unified biosphere spinning through the void. The planet's atmosphere glows with a thin blue line, the fragile envelope that protects all terrestrial life from the harsh environment of space. How does it feel to return home after this cosmic journey? Can you sense how your perspective has expanded, how you now see Earth and humanity's place in the universe with new eyes? Are you feeling that profound sense of connection to the cosmos, that understanding of how we're all part of this magnificent cosmic story? Pause for 3 seconds. Perfect. Let that cosmic perspective fill you with peace and wonder as we complete our journey. Chapter 29. Settling back to Earth cosmic perspective. Voice becomes gentle and grounding. As your cosmic journey draws to a close, you gently descend back through Earth's atmosphere, watching the planet's surface features come into focus. The lights of cities twinkle like terrestrial stars, connected by the bright threads of highways and transportation networks. Rivers wind like cosmic filaments across continents, and the boundaries between land and sea create patterns that echo the cosmic web you've just explored on the largest scales. You drift lower, approaching the region where you began this journey. Whether you're in a bustling city or quiet countryside, the landscape below takes on new meaning after your voyage through the cosmos. Every atom in the rocks, the air, the water, and every living thing was forged in the nuclear furnaces of ancient stars, scattered by supernovae, and eventually incorporated into the material that formed our solar system. The carbon in the trees and plants around you was created in the triple alpha process within the cores of red giant stars. The oxygen you breathe was forged in the final moments of massive stellar cores before they collapsed and exploded as supernovae. The calcium in the soil and in every living bone was synthesized in the silicon-burning shells of dying stars. You are literally made of star stuff, connected intimately to the cosmic processes you've just witnessed. As you settle back into your physical form, lying comfortably in your bed or chair, take a moment to appreciate the incredible journey you've just completed. In the span of a single evening, you've traveled from Earth to the very edges of the observable universe, witnessing stellar birth and death, exploring the architecture of galaxies, and contemplating the vast scales of cosmic time and space. The cosmic perspective gained from this journey puts earthly concerns into a broader context. The problems and stresses of daily life, while real and important on human scales, become part of a much larger story. The story of cosmic evolution that has been unfolding for nearly 14 billion years and will continue for billions of years to come. You are part of this cosmic story. Your existence represents the universe becoming conscious of itself, matter organized in such a way that it can contemplate its own origins and evolution. Through your awareness, the universe experiences wonder, beauty, and understanding. You are a way for the cosmos to know itself. The night sky above you, wherever you are in the world, contains all the wonders you've just explored. The stars you can see with the naked eye are mostly residents of the Orion Arm, your stellar neighbors within a few hundred light-years of Earth. The faint band of the Milky Way stretching across the sky represents your edge-on view of the galactic disk, containing hundreds of billions of stars and all the phenomena you've encountered on your journey. Every time you look up at the night sky from now on, you'll carry with you the memory of this cosmic voyage. You'll know that beyond the brightest stars lie vast nebulae where new stars are being born, ancient stellar graveyards where massive stars have ended their lives in spectacular explosions, and distant galaxies participating in the grand cosmic web that encompasses everything we can observe. The universe is vast beyond human comprehension, filled with wonders that challenge our understanding and inspire our imagination. Yet it's also intimate and personal because you are part of it. Every breath you take connects you to the atmosphere that protects all life on Earth. Every heartbeat pumps blood containing iron forged in the cores of ancient supernovae. Every thought represents the cosmos contemplating itself through human consciousness. What time is it now in your corner of the universe? Has this cosmic journey helped you release the tensions and concerns of the day? Are you feeling that deep relaxation that comes from contemplating the vastness of space and time, from understanding your place in the grand cosmic story? Pause for 3 seconds. Let that peaceful cosmic perspective carry you gently into sleep. Chapter 30. The Eternal Cosmic Dance, a Peaceful Ending. Voice becomes increasingly soft and soothing, guiding towards sleep. As you rest comfortably in your earthly environment, Carry with you the knowledge that the cosmic dance continues around you even as you sleep. The Earth rotates on its axis, carrying you through space at over 1,600 kilometers per hour at the equator. Our planet orbits the Sun at nearly 30 kilometers per second, completing its annual journey around our local star. The entire solar system moves through the galaxy at roughly 230 kilometers per second, participating in the grand rotation of the Milky Way. The galaxy itself moves through space, approaching the Andromeda Galaxy for their eventual merger billions of years in the future. The local group drifts through the cosmic web, following invisible currents of dark matter that have been flowing since the early universe. On the largest scales, space itself continues to expand, carrying distant galaxies away from us and stretching the fabric of reality. All of this motion, all of this cosmic activity, continues as you rest. You are a passenger on Spaceship Earth, traveling through the universe at incredible speeds while experiencing the profound stillness of sleep. The atoms in your body, forged in stellar cores billions of years ago, will continue their cosmic journey long after your current form has returned to the Earth and eventually to the stars. The hydrogen in your body remembers the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear fusion to create the light elements. The heavier elements remember the intense pressures and temperatures in stellar cores, where they were forged through the process of nucleosynthesis. Your calcium remembers the explosive moments of a supernova, when it was scattered into space along with all the other heavy elements essential for rocky planets and life. These atoms have been on an incredible journey through space and time to become part of you, and they will continue their cosmic odyssey long after they've served their current purpose. In this way, you are both temporary and eternal, a brief arrangement of cosmic material that can think and feel and wonder about the universe that created it. The stars you've visited on this journey continue to shine in the darkness above you. Rigel blazes with blue-white fire, gradually burning through its nuclear fuel reserves. Betelgeuse pulsates in its red giant phase, approaching the moment of its spectacular supernova finale. The Crab pulsar spins 30 times per second, its lighthouse beam sweeping through space with clockwork precision. In the star-forming regions scattered throughout the Orion Arm, new suns are condensing from molecular clouds, beginning their own billion-year journeys of nuclear fusion. Planets are forming in circumstellar disks, slowly accumulating from dust and ice into worlds that may someday harbor their own forms of life. The cosmic recycling process continues, turning stellar death into stellar birth, transforming simple hydrogen into the complex chemistry that makes life possible. The nebulae you've explored continue their ancient transformations. The Eagle Nebula's pillars of creation may already be gone, destroyed by stellar radiation, though their light still travels toward Earth carrying the image of their former glory. The Ring Nebula expands ever outward, its white dwarf core slowly cooling as it fades toward its final destiny as a cold, dark cinder drifting through space. Even the supermassive black hole at the galactic center, Sagittarius A*, participates in this cosmic dance. Though it appears static and eternal, it too will eventually evaporate through Hawking radiation, taking longer than the current age of the universe multiplied by itself countless times. In the unimaginably distant future, when all the stars have died and only black holes remain, even these last vestiges of matter will slowly fade into the quantum vacuum. But tonight, in this moment, the universe is alive with activity and beauty. Galaxies rotate majestically through space, their spiral arms trailing behind like cosmic pinwheels. New stars ignite their nuclear fires for the first time while ancient stars breathe their last. The cosmic web continues its grand expansion, carrying galaxy clusters ever farther from one another, while dark energy accelerates the stretching of space itself. You are witnessing this cosmic moment, this particular arrangement of matter and energy that will never be repeated exactly the same way again. Every second, the universe evolves into something new, and you are here to experience it, to be aware of it, to appreciate its beauty and complexity. As your breathing slows and deepens, imagine yourself floating once more in the peaceful void between stars, supported by the invisible currents of dark matter and cosmic expansion. The gentle radiation from distant galaxies warms you like cosmic sunlight, and the quantum fluctuations of empty space create a subtle massage that relaxes every cell in your body. You are held safely in the gravitational embrace of Earth, which is held by the Sun, which is held by the galaxy, which is held by the local group, which is held by the cosmic web itself. These nested levels of cosmic structure create a hierarchy of safety and belonging that extends from your bedside to the very edges of the observable universe. The cosmic microwave background radiation, the afterglow of the Big Bang itself, bathes you in photons that have been traveling through space for over 13 billion years. These ancient photons carry information about the early universe, when it was only 380,000 years old and first became transparent to light. As you rest, you are literally bathed in the light of creation itself. Let your consciousness expand to encompass all the scales of cosmic structure you've explored tonight. Feel yourself as an atom in the molecule of Earth, which is part of the solar system molecule, which is part of the galactic molecule, which is part of the local group molecule, which is part of the cosmic web molecule that encompasses everything we can observe. From this cosmic perspective, all the boundaries that normally separate things begin to dissolve. You are not separate from the stars. You are made of the same hydrogen and helium forged in the Big Bang, processed through stellar cores, and scattered by supernovae. You are not separate from the galaxies. You participate in the same gravitational dance that shapes cosmic structure on the largest scales. The universe is not something you observe from the outside. You are the universe observing itself from the inside. Through your awareness, the cosmos experiences wonder, beauty, love, and understanding. You are one way that the universe has learned to think and feel and appreciate its own magnificent complexity. As you drift toward sleep, know that you take with you the perspective of cosmic scales, the knowledge of your stellar heritage, and the peace that comes from understanding your place in the grand story of cosmic evolution. Tomorrow, when you wake, you'll still carry this expanded awareness, this deeper connection to the cosmos that surrounds and includes you. The stars will still be shining when you wake, continuing their ancient nuclear burning, their slow evolution through the stellar life cycle. The galaxies will still be dancing their gravitational ballet. The cosmic web will still be expanding, and the universe will still be creating new complexity and beauty with each passing moment. But for now, rest in the knowledge that you are part of something infinitely beautiful and mysterious, something that began with the Big Bang nearly 14 billion years ago and will continue for billions or trillions of years to come. You are a temporary arrangement of cosmic matter that has learned to contemplate its own origins and destiny, a small but precious part of the universe's journey toward ever greater complexity and consciousness. Sleep well, cosmic traveler. Dream of spiral galaxies and stellar nurseries, of supernova explosions and planetary nebulae, of the vast scales of space and time that make up our magnificent universe. Let the gentle rhythms of cosmic evolution carry you into peaceful rest, knowing that you are eternally connected to the stars, the galaxies, and the cosmic web that encompasses all of existence. In your dreams, you may continue floating through the Orion Arm, visiting distant worlds orbiting alien suns, witnessing the birth of new solar systems, or drifting through the ethereal beauty of emission nebulae painted across the cosmic dark. Or perhaps you'll dream of future journeys, when humanity has learned to travel between the stars, carrying Earth's precious heritage of life and consciousness to distant worlds throughout the galaxy. Whatever dreams come, carry with you the peace of cosmic perspective, the wonder of stellar evolution, and the profound knowledge that you are made of star stuff, participating in the universe's endless dance of creation and transformation. Sleep now, cosmic wanderer, held safely in the gravitational embrace of your home planet as it spins through the star-filled void of space. The universe dreams through you as you sleep, experiencing rest and peace through your consciousness, preparing for tomorrow's new discoveries and wonders. Rest well in the knowledge that you are home, not just on Earth, but in the cosmos itself, surrounded by the infinite beauty and mystery of existence. Good night, fellow traveler. May your dreams be filled with starlight and cosmic wonder, and may you wake tomorrow with eyes still bright with the magic of the universe we're all part of. Sleep peacefully in the Orion Arm, our home among the stars.